Okay, so statistical inference is a process of drawing conclusions about a population based on data from a sample of that population. Okay, so we've got a big population. Okay, we've got a big population, and we're gonna draw a sample of that population. So we're going to take a small group. We're going to take a small group of people from our big population, and we're going to find out information about them. So any quantity computed from the values in a sample is called a statistic. Okay, the whole branch of statistics, the whole mathematical branch of statistics is all based on gathering samples. The corresponding population characteristic is usually called a parameter. We gather information. We take a survey of East High students to find out who has a driver's license or who doesn't. That is a statistic. The actual data from East High School's office, taking every student and seeing if they have a driver's license, that would be a parameter. Parameter comes from like a census, if it's even possible. A lot of times, and as we move forward, the parameter will be something that we don't necessarily know. Okay, an unknown parameter that we're trying to estimate. Okay, since we use statistics to estimate parameters, statistics are also called estimates. A statistic is an estimate. Parameters are true values. This is super important. You'll have a test question about this. It'll say, describe the difference between a parameter and a statistic. Okay? This isn't the only time you're supposed to see this. If you don't read your book, you aren't going to see it again. If you don't look at all the vocabulary in the back, you're not going to see it again. If you don't reread your notes, you're not going to see it again. You got to know this. It's on the test. The question, what is the difference between a statistic and a parameter? A statistic is a value that comes from a sample. A parameter is a true value. It comes from the entire population. Statistic comes from a sample. It's an estimate. A parameter is a true value. It's the value that the entire population holds. All right, so the problem with using statistics to estimate parameters is that our estimates usually aren't correct. Okay, if I just sampled 10 people from East High and said, do you have a driver's license, yes or no, and 6 of them said yes, out of the 10, that's 60% that said yes, right? Do you suppose that's the same as the exact number, true percent of East High students that have a driver's license? No, probably not. If I take a different sample, so I took a different sample, okay, my first sample I got 60%, 6 out of 10 had their driver's license. The second sample I got 4 out of 10. Is that one correct? Is that the same as the exact percent? No. I could keep taking samples all day long, just different samples of 10. Am I always going to get the same value? No, maybe the next time I do it I get 6 out of 10 again, and then I get 5 out of 10, and then I get 3 out of 10, and then I get 7 out of 10. Maybe I was in the senior hallway that time. So I can take different samples and get different values every single time. You could all go out into the school and get a sample of size 10, right? And ask each of those 10 people, do you have your driver's license? Would you all come back in with the same number of yeses out of 10? No. Okay? Now I'm building up. This is important. The fact taking more than one sample is an important thing that we're leading up to when we talk about sampling distributions. And realizing that not every sample is going to have the same value. All right? Okay, so the problem with using statistics to estimate parameters is that our estimates usually aren't correct. And they're all different. Okay, for example, suppose we know the mean height of all East High students is 65 inches. Okay, we have everyone's height here at East High. We averaged it all. The average height is 65 inches. If we were to take a random sample of 50 East High students, you're not going to get exactly 65 inches. Tommy, you may go out and get the mean is 63.8. Okay, Griselda, you'll go out and you'll get an average of 65.4. Who's right? Okay, well, you're both right for your sample. For your sample, you're correct. Okay, you can't control over the sample. Okay, so you get a bunch of samples. That's still not exactly the true mean. So the problem with statistics, what I need you to realize is the problem with statistics and with samples is that we're trying to estimate this value. We're trying to figure out the 65 inches without doing a census. okay? And we do it based on a sample. And the problem is our samples aren't going to give us that exact value the first time, okay? Or the second time or the third time. What it has to do with, the way we make statistics work is we take lots and lots of samples of the same size. So I'm going to go out and it's the idea of it. You actually aren't going to do it. Somebody's already explored this entire concept. Instead of, you will be allowed to go out and just take one sample of 50, okay? Because of what's called the central limit theorem, if you read about it. So it's okay that ours aren't exactly the true value, okay? We have testing, we have procedures and things that we can go through to see how far off we are we close enough, that kind of thing. So the next step, the question we need to answer is how good is our estimate? How good was my sample of 63.8? How close was it? Okay, so since the value of the statistic or estimate depends on the sample selected, the value of the statistic will vary from sample to sample. This variability is called sampling variability. Okay, we're going to use the word sampling a lot in the next few sections of notes. Okay, so that variability is called sampling variability. Please try to understand it. It's not that hard. You know, these two samples from right up here, are they different? Okay, variability means varies. Isn't the base word for variability vary? Doesn't vary mean different? Changes? Okay, so sampling variability simply refers to that if each of you went out and took a sample of size 50 students and got their heights, that you'd all get different samples. Your average height would vary. You would not all get the same thing. Does that make sense? That's sampling variability. So sampling variability is different from other types of variability. Okay, so if X equals the height of an East High student, then X has variability. Different students have different heights. This is not sampling variability. Okay, I'm trying to explain the difference between regular variability and sampling variability. Okay, if I just look at each of you individually in here, aren't you all different heights? Could possibly some of you both be the same height? Yeah, you could be. Okay, but your heights vary. Your individual heights vary. That's not sampling variability. Sampling variability, okay, X bar is the average height of a sample of 50 East High students. Then X bar also has variability. Different samples will produce different averages. This is sampling variability. Okay? So now, instead of just looking at each of you individually and saying you have different heights, so your heights vary, your heights have variability, that's just plain old variability. Sampling variability, if I pulled 3 of you up here at a time, pulled 3 of you up here, got all your heights and averaged them. Got 3 more of you up here, found your heights and averaged them. Do you suppose they would all be the same average? No. But I got those averages by taking samples of size what? How many people did I pull up here at once? 3. So I took samples of size 3 and found an average height. This is sampling variability, where you take different samples. It's like if I sent each of you out to get a survey of 10 different people, and you'd come back with different averages. 6 out of 10 said they had a driver's license. That's sampling variability. Okay? So statistics or estimates are variable while parameters are constant. Okay? The population at East High, the percent of people that have a driver's license or the average height, that's something that remains the same as long as all the same students are at East High. Okay? Our samples, our estimates are always going to be different depending on the sample I get. Okay. So the distribution of a statistic is called its sampling distribution. Okay, so there's lots of different statistics. Okay, so the different statistics, we could find the mean. That's one we talk about a lot. Okay, the sampling distribution of a mean, of the sample mean. Okay, so I could get different samples of size 10 and find the mean of all of those. And that would be the sampling distribution of the mean. Could I get different samples of size 10 and find the mode? The mode, like the height. What height occurred the most often? I could have the sampling distribution of the mode. Could I take samples of size 10 and find the standard deviation? Yeah. Is standard deviation a statistic that you can calculate? Yes. And then I could find the sampling distribution of the standard deviation. I could see how the standard deviations are different for each sample that I got. So in real life, we just take one sample and hope we get a good one. Okay? But to see what that tells us about the population, we need to know what we can expect from different samples from a particular population. Statisticians have already explored what different samples look like, what happens when you take repeated sampling of the same population. And we're going to actually look at in the coming days some things for that. So we need to see how the sampling process behaves. We need to ask, what if we had a different sample? How much variability does the estimate have? What does its distribution look like? Distribution, remember, is a picture of the graph, like a histogram picture or just a list of all the numbers. Note, the important features of a sampling distribution are its shape, center, and spread. We had that back in chapters 1 through 6. If you describe a distribution, you describe its shape, center, and spread. All right, next page. So now we're going to start looking at sampling. Okay, this is an idea. I want you to remember, you know how I said we were going to take 3 people up and calculate their heights? Measure your heights. I was going to pick 3 of you, measure your heights, and then find the average height. Okay, we're going to do that with a group that's already determined here. Something. Okay. And we're actually not going to do this page. Well, I don't know if I need to do this page or not. So, well, yeah, let's do this page. Okay, so suppose that our class is the population and we're taking samples of size 3 to estimate the true mean hours of sleep for students last night. So X is the hours of sleep. Yep. So X is the hours of sleep last night, and X bar is the average hours of sleep last night for 3 randomly selected students. So I need to know all of your hours of sleep. So Tommy Herman, tell me, you just think about it. Jacob? Yes, you should. You're going to want to write all this work down. So no, you don't. No, please just stay with me. Be quiet, please, and listen. Because just write the. I guess it really doesn't make any difference. Let's just list everybody's hours of sleep. So hours of sleep. We don't need. Start over here. Last night. 5. 6. 7. 5. Griselda. 6. Okay. 7.
Yeah.
6. Mitch. 5. 7. Okay. So here's a list of all of our average hours of sleep. So I'm just going to number these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Now I'm actually not going to do this entire thing, but here's an idea of a sampling distribution. These are all hours of sleep, right? Hours of sleep. That's what X is. X is the hours of sleep. Okay, so what I'm going to do, this is an idea of a sampling distribution. I'm trying to demonstrate for you the idea of a sampling distribution. So I'm not going to do all of these, but I'm going to do a few of these because all of these is a lot. If I do 10 choose 3, or 11 choose 3, 11, and I wanted to choose all groups of 3, that would take me a really long time. You could do NCR 10C3 on your calculator, and that would give you how many. So what I'm going to do is I'm going to select, randomly select, so go math, PRB, random integer. You don't have to do this. You don't need to do it. Okay, I'm just going to show you. I'm going to choose a number from 1 to 11. And I'm going to choose 3 of them. And so this gave me 6, 5, and 3. So the 6th person had 6 hours of sleep, the 5th person had 6, and the 3rd person had 7. So I'm going to add those up and divide by 3. So add those up. That's 12, 19 divided by 3 is 6 1/3 hours of sleep. And that is X bar for this sample.